explain about why it is important to consider heterogeneous and random data traffic in wireless networks. And the second part is a brief introduction to stochastic network optimization. So I will briefly explain what is the standard form of a stochastic network optimization problem and how we can use Lyapunov optimization theory to solve these kind of problems. Then I will give two explicit examples about the applications of the Lyapunov optimization theory. The first example is dynamic resource allocation in massive MIMO systems. And the second is optimizing information freshness in a multiple access channel with heterogeneous traffic. So first, let's take a look at the performance objectives of mobile networks for 5G and beyond. So this figure comes from this document called Framework and Overall Objectives of the Future Deployment of International Mobile Teletraffic for 2020 and beyond. And you can also find similar type of figures in other documents, but mostly the main messages that they contain are more or less the same. So as we can see from this figure, that depending on the use cases of mobile communication, the performance objectives that we care about are very different. So for example, for enhanced mobile broadband, we care about area spectral efficiency and peak data rate and experience data rate and spectral efficiency. And then for ultra reliable and low latency communication, we care more about latency and mobility. And for massive machine type communication, we care more about the connectivity. So there are several important properties of mobile data traffic that are very often overlooked in the current literature. The first is randomness, because mobile data are generated in a random manner, and when the data is traveling through the network, they will arrive and depart from network nodes in a random manner too. So this will lead to queue dynamics. And if we do not consider the queue dynamics, we can very often have deterministic resource allocation schemes, and these kind of deterministic schemes are very often suboptimal because they do not take into account the queue dynamics. And the second property is the heterogeneity of data traffic. So we want to evaluate the performance of a network. There is no unified performance metric for all kinds of data, because for different type of data, we will need to consider different type of metrics. For example, for enhanced mobile broadband, the data are mostly rate-oriented. And for some delay-sensitive applications, such as remote surgery, then we care mostly about the delay. Then for some systems that cares mostly about information freshness, then those data will be age-oriented. The third property is the reusability. Many mobile data contain content that are highly reusable, such as videos in video on-demand applications and training data for machine learning, for example. So in this talk, I will focus mostly on the first two properties, which are the randomness and heterogeneity. And if we start from the first one, random data traffic. When we consider random data traffic in a wireless network, and we want to design a resource allocation for such kind of dynamic network, and this optimal resource allocation in a dynamic network can very often be formulated as a stochastic network optimization problem. So in the next part, I will give a brief introduction about stochastic network optimization. So what is the stochastic network optimization problem, and how it differs from a typical convex optimization problem, for example? So for typical convex optimization problem, we have a set of variables to be optimized, which are x1, x2, until xa. Now we can write it in a vector form x. So the objective is to optimize some convex function f0 of the variable x, subject to some convex constraint of inequalities and equalities. But in a typical stochastic network optimization problem, we intend to find the optimal control actions which are different in each time slot. So the variables that we want to optimize are a sequence of control actions for each network node in each time slot t. And our objective is to minimize some long-term time average expectation of a performance objective which depend on the control actions in each time slot, with some constraints which are some long-term time average inequalities and time average equalities, and with an additional constraint that all the network queues are stable. So before showing how to solve this problem, I would briefly talk about queue stability and what it means to have a stable queue. So let us consider the following single server discrete time queue with the input or arrival process AT and output or the server process BT. So here AT
if I may interrupt, just
yes.
one question. So you spoke about heterogeneity as part 2. I mean, one of the things that you cared for. Now, when you talk about heterogeneity, are you going to do something which is joint optimization of all several different things together?
Yes. So in the last part of this talk, I will show optimization problem when the performance objectives and the constraints are based on different performance objectives of different users.
Okay. And in the stochastic optimization problem that you mentioned, are you still going to assume certain forms of convexity on the f functions? I mean, you're interested in the long-term averages, but are you going to assume any f's?
Yes. Yes.
Okay.
So yeah. So this function f0 has to be if it's minimized, then f0 has to be convex, and if it's maximized, then it needs to be concave.
Okay.
Yeah.
Right. Thank you. Yeah.
Yes. So so AT, the arrival process, AT denotes the amount of new data arrivals in each time slot t, and BT denotes the amount of data that can be processed in slot t. And here QT denotes the backlog, which is the amount of data waiting to be processed. And the queue evolution can be described by the following dynamic equation, which means that the queue size in the next time slot t+1 would be the sum of the remaining data in this slot plus the newly arrived data in slot t. Or it can be written in an equivalent form with this b tilde t, which is the minimum between qt and bt. So it means the actual processed data in slot t. And we say that a discrete time process qt is strongly stable if the long-term time average expectation of the queue size is finite. And just one more word about the strong stability. So when a queue is strongly stable, it means that we will have finite queuing delay. That for all the data that arrived in this queue, they will be processed within finite amount of time.
Understand? Yeah, sorry to interrupt again. Just to understand.
No problem.
Weakly stable notion in this context.
So there are 3 different forms of stability. One is rate stable, and then mean rate stable, and then strongly stable.
Okay.
But
and this is the strong
one? Yes, it is just this term is just called strongly stable, but actually this strongly stable can be used later on in this stochastic network optimization framework, that where we can very often show that the queues are strongly stable. But actually in those constraints here, when we say stability, it can be also mean rate stable.
So what would that mean? So like you explained, you really want that every packet should be serviced in finite time. So what would be some other notion of stability with respect to, say, a packet? Would it be an
So
average?
for example, if we want the queue to be mean rate stable, it means that the arrival rate would be smaller or equal to the time average departure rate.
Okay.
And mean rate stability has a different form. It actually can be written as limit of the expectation of Q over T goes to 0 when T goes to infinity. So usually this strongly stability is the stronger form of stability.
Okay. Thank you.
You're welcome. So let us consider a system with k users, and each user has a q denoted by qkt. And here qt is the vector of all the q's in the system. And each q is updated by this dynamic equation where both the arrival process and server process, ak, bk, are some general functions of the control variable alpha t and the random event omega t. So this random event can be any event that varies over time, such as randomness in the channel or new data arrivals. And let us define a collection of real-valued attribute vectors, yt and et, which are also functions of the control action alpha t and the random event omega t. And let us define a omega t as the set of all possible control actions given the random event omega t. If we define YL bar as the time average expectation of YL and EJ bar as the time average expectation of EJ, then we will have a problem that intends to minimize the time average of Y0 subject to some constraint, time average constraint on YL and time average constraint on EJ, and that all the network queues are stable. So in order to solve this kind of stochastic network optimization problem, we will use Lyapunov optimization theory. It is very often used to solve problems that optimizes time average of some performance metric subject to time average constraint on some other quantities. So first, we need to transform all the inequality and equality constraint into Q stability problems, because a Q is mean rate stable if the time average arrival rate is smaller or equal to the time average service rate. So all the inequality and equality conditions can be transformed into Q stability problems by considering these following dynamic equations. So if we consider virtual queues ZL and HJ, where ZL is updated by this equation and HJ is updated by this equation. And we can show that when these virtual queues are stable, we will always have those constraints will be satisfied. Both the inequality and the equality constraint will be satisfied. So let us define theta t as the combined vector of all the queues in the system, which include the data queue, qt, and the virtual queues, zt and ht. First, we can define.
Sorry to
yes,
interrupt.
please.
Yeah, I just had a question. So can you get a sense of what the virtual queue here really is? So I didn't quite understand what the virtual queue is.
Yes. So as I have written here, the virtual queues are used to transform the constraint into Q stability problems. So here, for example, in order to have this ZL queue stable, then the time average arrival rate has to be smaller or equal to the time average departure rate. So the arrival rate is 0, and the departure rate is time average of minus YLT. So if the Q is stable, then we'll always have that 0 is smaller than time average of minus YLT, then which will give us that time average of YL will be smaller than or equal to 0.
Okay, okay, yes. So capital Z and capital H's are really, so you take each of these constraints and you construct these two virtual queues. So it's going to be
Yes.
a virtual queue for every constraint that you have in.
Yes, so for every constraint, so in total we will have L plus J virtual queues.
Okay, okay.
If we
Yeah,
have
thank you.
L plus J constraints. Yeah,
Okay.
that was a very good question. Thank you. So first we will define a Lyapunov function, which is a scalar measure of the congestion level in the system. And the quadratic form is very commonly used. So for a given network Q state theta t, we define the Lyapunov function as the sum of the squared Q sizes.
Sorry to interrupt again. So I'm sorry to
Yes,
interrupt again. There's a question from the audience. So
yes,
the question is, does the Q stability of the all set of Qs? So I'm guessing he's talking about the Q stability for all the virtual Qs solve the original optimization objective.
no, those conditions are only used to ensure that these constraints are satisfied. So the performance objective will come in a different way, which I will present later.
Okay, yeah, thank you.
Yes. So the Lyapunov function can be written as the sum of the squared Q sizes for all the Qs in the system, including the real Q, Qk, and the virtual Qs, Zl and Hj. Then we can define a one-slot conditional Lyapunov drift, which measures the difference of system congestion level between two consecutive slots. So this theta t is given as the expectation of the difference between the Lyapunov function in slot t plus 1 and in slot t, conditioning on the network Q state theta t. And intuitively, if we can minimize the Lyapunov drift in every time slot, then the Qs will be eventually stabilized. Then we can define a function called the drift plus penalty function, which is the sum of the Lyapunov drift plus a penalty function, which is associated to the performance objective that we want to optimize. So y0, as you might recall, is the performance objective function that we want to optimize. And we add a non-negative control parameter v here, which determines the weight on performance optimization. So the intuition behind this drift plus penalty is that by jointly minimizes the Lyapunov drift and the penalty function will be able to achieve system stability and approach the optimal solution to an arbitrarily close level. So if after minimizing the drift plus penalty term which is shown in the previous page, we can get the following algorithm. In every time slot t, we observe the current state theta t and the random event omega t, and then we make a control decision alpha t that solves the following problem. So we intend to find alpha t that minimizes this expression. So I will explain about what each term in this expression means. So the first term is v times y0, which is the performance objective function, which in each time slot t, which are functions of the control action and the random event. And the second term is related to the real data queues, QKT. And here AK and BK are the arrival and departure processes. And the third term is related to the virtual queues that are associated with the inequality condition. And the last term is related to the virtual queues that are associated to the equality condition. So this expression might seem long at the first look, but actually in many cases it can be very much simplified. And the complexity of the algorithm would depend on the functions A, B, which are the arrival and departure processes, and Y, L, EJ, which are the objectives and constraints. And in some cases, the solutions can be very simple, and we can obtain closed form solutions for the control
One
actions.
question here. Sorry to interrupt again. So how
No
sensitive
problem.
it is to the choice of the penalty function? And are there, so just like you said, the quadratic choice for the Lyapunov function is pretty standard. Are there like standard candidates for the penalty? Like, is this one of the many possible?
Yes, so the penalty function is always associated to the performance objective function. So if we have a look at the problem formulation, if we want to optimize the time average of y0, then we put the expectation of y0 t here, conditioning on the network state q, and then we multiply it with the control parameter so that we can.
It's just a constant here. It's not a random variable.
V is a constant, yes.
Okay.
So the larger V we have, it means that we want to approach the optimal solution as much as possible. But V will also increase the congestion level in the system.
Okay, yeah, thank you. I misunderstood that as a random variable actually, sorry. Go on.
Thank you, that's a very good question too. So it's a constant value that we need to choose beforehand. So in the following, I will give two examples about the applications of Lyapunov optimization theory and this mean drift plus penalty technique. The first one is dynamic resource allocation in massive MIMO systems. So I think some of you, maybe probably most of you know already what is a massive MIMO system. But in case someone is not familiar with this, I will just give a brief introduction. The Massive MIMO stands for Massive Multiple Input, Multiple Output. And it is a key wireless access technology for 5G and beyond. And the key idea is to let the base stations be equipped with large arrays of many antennas. And those base stations with large antenna arrays will serve a large number of user terminals simultaneously by spatial multiplexing. But the number of users being served need to be smaller than the number of antennas. And such kind of systems are shown to achieve very high spectral efficiency and energy efficiency. And there are some nice characteristics that are offered by Massive MIMO technologies. When the number of antennas goes to infinity, then we can observe two nice properties. The first one is channel hardening, which means that the channels between the base station and the users are almost deterministic as if there isn't any fading in the channel. And the second one is called favorable propagation, which means that the channels between two users, the channels from the base station to two different users would be nearly orthogonal when the number of antenna goes to infinity. So we can spatially separate different users in the system. And for those who are interested in more details about Massive MIMO, you may check the following two books. And the first book is Fundamentals of Massive MIMO, which is co-authored by my supervisor, Eric Larson. And the second is Massive MIMO Networks, Spectral Energy and Hardware Efficiency, which is co-authored by my colleague, Emil Bjornsson. And in our group, we are also managing a Massive MIMO blog, where you can find many interesting information and posts and discussions about Massive MIMO. So here I will present part of my work that has been published recently with the title Dynamic Resource Allocation in Co-located and Cell-Free Massive MIMO. So the main motivation of this work is that most of the conventional power control schemes in Massive MIMO assume that there are infinite amount of data to be transmitted. But in reality, this case is very unlikely. And most of the existing power control schemes are optimized based on achievable ergodic rates, and it is fixed over the entire transmission period. So it's kind of deterministic power control scheme. Then when we consider a Massive MIMO network where the nodes are randomly generating data traffic, how we should design an efficient scheduling and power control scheme. So we consider the following single cell uplink Massive MIMO network with M co-located antennas at one base station and K single users, single antenna users. And let BKT denote the uplink data packet that are generated from user K in slot T. And let LKT denote the data in the transport layer reservoir that are waiting to be admitted in the system. And QKT denotes the amount of data in the transmission queues waiting to be transmitted over the physical layer channel. And we also have AKT here, which are the amount of data that are allowed to be admitted into the transmission queues in each time slot. And RKT denote the physical layer transmission rate. So for each user, we need to determine first how much data we will allow to be admitted into the system, and how much transmission rate we should allocate to each user. And if we consider a single cell Massive MIMO with block fading channels and IID relay fading, the maximum achievable ergodic uplink rate can be lower bounded by this expression, which is the log2 1 plus signal to noise plus interference ratio, multiplied with tau c minus tau p, where tau c is the coherence block length and tau p is the payload signal length. So tau c minus tau p is the length in the coherence block that are used for data transmission. And
sorry to interrupt. So one question
yes.
here is the fading state. These are all received. Channel gains are all known and fixed upfront, and they're known to everybody, or are these only known at the receiver?
Excuse me, I didn't follow your question.
Yeah, my question was, sorry, I'll repeat that. My question was, since it's a MIMO channel, you talk about channel gains. So are these known at the receiver, or are these fixed throughout time?
So the receiver here would be the base station. So the base station, what the base station does is that the users will send pilot signals, and then at the base stations, it will do some processing and then get some channel estimate. And then it will use the channel estimate. Here we will use the channel estimate to calculate the achievable ergodic rate. So this ergodic rate is an average rate that can be achieved, averaging over different realizations. So it's not an instantaneous data rate.
And it is good enough that the receiver will estimate the state, and does it have to communicate it back to the users, or it's not?
No.
Does not transmit our allocation?
No, it doesn't need to be communicated back to the transmitter, because the most, as I have mentioned before, one of the nice properties of Massive MIMO is that it has this channel hardening property, so that the channel is almost deterministic. So it's like we don't have any small scale fading anymore, and and this achievable ergodic rate is only given as a function of the large scale fading coefficient and some channel estimates, and then the power levels of the payload and signals and the payload signals.
Okay, thank you.
Yes, so with maximum ratio combining, the SINR of user K is given in this expression, and with zero forcing, the SINR is given in this expression, and both of them are only functions of the large scale fading beta K or beta J, and the mean square of the channel estimate gamma K, and then the power levels that we allocate to the payload signal and to the payload signals. So for each user K, its transmission queue is updated by this dynamic equation, where AKT is the amount of data that is allowed to be admitted into the queue, and RKT is the amount of data that can be transmitted over the physical layer channel. And let lambda K denote the average data arrival rate, which is the expectation of BK, and let RK denote the time average expectation of the admitted data rate of user K. So our intention is to solve a problem that maximizes some element-wise non-decreasing concave function f of the time average admitted data rate R, subject to two constraints. The first constraint is that the average admitted data rate is no larger than the average generated data rate, which makes sense because you cannot transmit more than what you have. The second constraint is the Q stability constraint. And here the control actions that we have for this problem are AT and PT, where AT is the amount of admitted data in each queue, and PT is associated to the power levels that we allocate to each user. First, we need to introduce some auxiliary variables, new t and virtual queues yt, that update as follows. So the input process of the virtual queue is the auxiliary variable, and the output process is the amount of admitted data rate, AKT. Then we can show that the original problem, which has maximizing some functions of time average, can be transformed into an equivalent problem that maximizes the time average of the function, subject to some time average constraint. Then after having this form, we can use the standard techniques from Lyapunov optimization theory by using the drift plus penalty and minimizing the drift plus penalty expression. And it's important to note that here we have an additional constraint on the auxiliary variable, that it has to be smaller or equal to something. And this A max is a sufficiently large upper bound for new KT, because all the control variables in this stochastic network optimization problem needs to be bounded. So when we introduce an auxiliary variable, it also needs to be bounded. Then for this problem, we can define the following Lyapunov function, which is the sum of the squared queue sizes, where the first part is the transmission queue sizes qk, and the second part is the virtual queue yk. And here eta is the weight factor on virtual queues. Then after some derivations, we can show that the drift plus penalty is upper bounded by this expression, which has 4 different terms. The first term is a constant term, and which is denoted by C. And then the remaining 3 terms are associated with different control variables. For example, the first term only depends on the admitted data process AKT, and the second term only depends on the auxiliary variables new KT, and the third term only depends on the physical layer transmission rate RKT. So we can solve these 3 sub-problems separately, and then we will have an algorithm as follows. So in each slot T, we first determine the auxiliary variables as solution to this expression. And in some specific cases, such as, for example, if this f function is associated to maximum fairness or maximum sum rate or proportional fairness, actually we can have closed form solution expressions for the optimal new KT. Then we decide the amount of data to be admitted to the transmission queues by this condition. So the intuition between this condition is that if the virtual queue is more congested than the transmission queue, then we will push more data to the transmission queue. Otherwise, we will hold the data in the transport layer reservoir. Then the third step is to determine the power control scheme by solving the maximum weighted sum rate problem. And here the weight on each user is equal to the size of its transmission queue. Then we will update all the queues and repeat these steps in the next time slot T+1. So this is an iterative algorithm where in each time slot we need to solve these 3 sub-problems. And in order to show the performance of the proposed algorithm, we have performed simulations to for single cell uplink massive MIMO with m equal to 100 antennas and k equal to 10 users, and coherence interval is equal to 100, and the pilot length is equal to the number of users. And we consider the data arrival process as a Bernoulli process, where the packet size is equal to 5 times the coherence block length. And we have randomly generated the locations of 10 different users. And here we have ordered the signal-to-noise ratio of these 10 users in increasing order. We have also applied some heuristic algorithms for comparison based on the optimization method in the reference shown at the bottom of this page, which is called optimal payload and payload power control in single-cell massive MIMO systems, which are also written by my former colleagues. So here is the, which presents two figures that shows the time average delay of each user when considering max-min fairness and maximum sum rate as the performance objectives. But here the DSA means dynamic scheduling algorithm, and this DSA with MMF means that we apply the dynamic scheduling algorithms with the performance objective function that is the max-min fairness. And here DSA with MSR means we apply the dynamic algorithm with the performance objective to maximize the sum rate. And we can see that in both figures, our dynamic scheduling algorithm can guarantee finite delay when the arrival rates are within the network capacity region. But for the other heuristic algorithm, some of the user queues would be unstable, so their time average delay would increase with time, and it will be infinity as time goes to infinity. So it shows that dynamic scheduling algorithm in a network with random data traffic has the advantage to be able to achieve system stability if it can be stabilized. And this cannot be guaranteed with some other heuristic algorithm which does not take into account the queue dynamics. The second example that I will show is optimizing information freshness in a multiple access channel with heterogeneous traffic. So the information freshness is characterized by a newly emerged metric called the age of information, and which is very often abbreviated as the AOI. Let us consider a stochastic process that is being observed by a source S that generates some samples containing the status update about this source. And this data will enter a queue and then afterwards being transmitted to a destination. And assume that the packet arrival rate is lambda and the service rate of the queue is mu, then the throughput of this system is the minimum between lambda and mu. And if the queue is stable, the delay per packet can be given by this expression. But however, neither the throughput nor the delay can capture how fresh are the data samples received at the destination node. Therefore, the age of information has been proposed as a new metric and tool that characterizes data freshness and timeliness of an information flow. The AOI measures the elapsed time since the generation time of the last received status update. So let's the data T denotes the AOI. It is equal to T, which is the current time slot, minus GT, which is the generation timestamp of the last received update. If we consider a continuous time case, then the age would evolve as in the figure on the left side. So the age increases, and then until there is a successful reception of the status update, then it will drop to a value that is equal to the difference between the generation time and the reception time of the last received update. And in the discrete time, the age evolution is also similar, except that the age takes discrete values. So it increases by 1 after each time slot, and then it drops to a certain value when there is a successful reception of the status update. The system we consider...
One question.
Yes.
So the drop on the left plot, the drop in the age is proportional to the size of the packet. Is that the correct way to think about it? So it's like, yeah, in your figure, I'm just trying to understand the drop that happens, let's say,
yes.
at T1. So what is the size of the drop?
So it drops to a value. For example, if we take a look at this peak, then it will drop to a value here, which is equal to the difference between T3 and T3 prime. So T3 is the generation time of the third packet, and T3 prime is the reception time of the third packet.
Okay, okay, got it. Yes.
So the age measures like how old is your last received status update.
Yes, okay, yeah, got it. But yeah, also actually one question. So the sawtooth curve that you have, right? So if you look at the peak of the sawtooth curve and the drop for which it starts again, so that's the solid black line that you have. Just the that drops down and comes back again. What is the size of that? Like, does it? So in your figure, is it corresponding to the size of the? How should I put this? Yeah, I don't think I'm able to describe this correctly. It's the small black portion that corresponds to the drop size. So what you explained, T3 is the size of the triangle, right? The length of the triangle sides. How about the solid line? Yeah, exactly. The one that you're just marking out.
Oh, so the age drop in each peak after each peak. You mean this part?
Yeah, yeah.
I think so. If the age drop here, if you determine here as T, then the difference would be T minus T3 prime minus T3.
Oh, it's still okay. Oh, it's okay. So the right way to think about it is generation time and the time it's received at the receiver, and the difference is the overall drop. Okay, then I think you had answered my question.
Yes, thank you. So we'll consider the following system as a way to show how we can optimize the network performance with heterogeneous traffic.
Sorry to interrupt. I'm sorry to interrupt again. So there is somebody has a question here. It's about the age of information metric itself. So the question is that does the drop signify the inverse notion of packet size? So
packet size. I think all the packets are the same size.
Yeah, so I think if you just pay attention to what Dr. Zheng just mentioned, I think that might have answered your question. The drop signifies essentially the difference between the generation and the reception time at the receiver. Okay, he's got it. Thank you. Yeah, please continue.
Now, the drop time determines how much difference is your current time between the difference of this time. So when you have a peak here, so this part is equal to T3 prime minus T3, but here, the drop time, you need to take a look at your current time slot and then deduct this part from it. So what we know is that after there is a successful reception, the age will always drop to a value that is the difference between the generation and reception time of the packet. But this absolute value of the drop would depend on how is your assumptions in the system. Because for example, here I only consider the linear case, but there are also some other papers who have considered nonlinear age. So the linear can be nonlinear age. For example, it can be like exponential function or some power law function of the time. Then it is more difficult to characterize the drop after each peak.
Follow up on that. So why would you have a nonlinear growth in the time? Like, what is the intuition for that?
I think the nonlinear age growth can be used to characterize, for example, if you consider in the case with remote surgery, the critical level is not like linear with time. Actually, the more time you delay, the more serious mistakes they will make in the system. So you can consider an age that is not linear, but it increases faster than linear to capture this urgentness of your application compared to the time.
Okay, that's interesting. Okay, thank you.
You're welcome. So let us consider a time-slotted multiple access channel with two source nodes transmitting to a common destination D. So here we call it a MAC channel with heterogeneous traffic because first we consider different type of power supplies for the two nodes. So S1 is connected to a power grid. But S2 only relies on energy harvesting as the power source. And we assume that the energy arrives in this node S2 following a Bernoulli process with probability data. And not only their power supplies are different, their data types are also different. So we assume that S1 needs to transmit, and S1 has some data queues which contains the data packets that need to transmit it to the destination D. And these data packets are generated with arrival probability lambda. But for the energy harvesting sensor, since it is measuring some stochastic process in the environment and it needs to keep its information as fresh as possible. So it will generate a fresh data sample before each attempted transmission. And we assume that the destination node has multi-packet reception capabilities, which I will explain with more details what it means. So since the first node contains a data queue which maintains a data queue which contains the data that needs to be transmitted, we apply first in and first out policy. But for S2, it will always generate a fresh sample before each attempted transmission. And in case of failed transmission, S1 will retransmit the same packet in the next slot, because all the packets needs to be transmitted to the destination correctly. And S2 will drop that failed packet and generate a new sample before the next attempted transmission. So it only generates fresh samples and transmits to the destination when they had the chance to. And the evolution of the data queue at node S1 and the energy queue at node S2 can be described by the following dynamic equations. So here, A1, A2 are the data arrival and energy arrival processes. And B1 is the successful reception process. And ST is the event of transmission. So whenever there is an attempted transmission, one energy chunk is removed from the energy queue of node S2. And multi-packet reception means that the receiver can decode multiple packets from simultaneously transmitting sources, which are possibly interfering with each other if the received signal to interference plus noise ratio is higher than a threshold. So if we consider the case with two users and with small-scale channel fading, H and beta as the large-scale fading, and sigma square as the noise power, then we can derive the success probabilities Pi/I, which is the success probability when only node I is active, and Pi/Ij, which denotes the success probability of node I when both nodes are active. So in our case, the age evolution is can be described by this figure. Here, since we consider time-slotted system, the age evolution, it takes discrete values and it increases by 1 after each time slot. And when there is a successful reception of the status update, since this update is always generated right before that slot, so the age will always drop to 1 because the age of the newly received packet is always equal to 1. So we can write the evolution of the age by this dynamic equation, where TST denotes the successful reception event at time slot t. So when TST is equal to 1, age increases by 1 in the next time slot. If TST equal to, if TST equal to 0, which means that the transmission fails, then the age increases by 1 in the next time slot. If TST equal to 1, then the age in the next time slot will be equal to 1. And then we can define the average AOI as the time average expectation of the age when t goes to infinity. In each time slot, we have 4 possible scheduling actions, which are 1, 1, which means when both of them are transmitting, and 1, 0 when only node S1 is transmitting, and 0, 1 when only node S2 is transmitting, and 0, 0 when neither of them is transmitting. So we formulate this average AOI minimization problem with stability constraint. Our objective is to minimize the average AOI of node S2 subject to the Q stability constraint of node S1. And we have applied 2 different policies to solve this problem. The first one is a stationary randomized policy, where the random access decisions are made at each user independently based on some stationary probability distribution. And the second policy is drift plus penalty policy, where we will use Lyapunov optimization theory with virtual queues and drift plus penalty. So for the DPP policy, first we will define the network state phi t, which contains 3 variables. The first is the AT, which is the age in current slot, and HT is the battery status of the energy harvesting node, and QT is the queue size of the grid connected node. And we define the Lyapunov function as the squared data queue size of node S1. Then we define Lyapunov drift as the expectation of the difference of the Lyapunov function between 2 consecutive slots conditioning on the current network state phi t. We choose the penalty function as the expectation of the age in the next slot conditioning on the network state in the current slot multiplied with this non-negative control parameter v. So based on this drift plus penalty expression, we can derive that the drift plus penalty is upper bounded by the following expression. So the first 3 terms does not depend on our control action, and our control actions V1, our control actions will only affect the last term. So the mean drift plus penalty algorithm would give us the following policy. In each slot t, we will check for all possible values of the scheduling decision ut, and we will choose the one that maximizes this expression. And the dynamic scheduling algorithm for this case will be given as follows. First step is the initialization, and then at each slot t, the network scheduler observes the queue size, the current age, and the battery status, and it makes a scheduling decision by solving this problem. Then we will update the data queue, the energy queue, and the age of information as follows. Then we will repeat those steps for the next time slot t+1. So here in the simulation results, we will show the average AOI versus the energy arrival probability data obtained with both the stationary randomized policy that has been optimized and the drift plus penalty policy. And on the left-hand side, the results are obtained with weak MPR capability. And on the right-hand side, the result obtained when the destination nodes has strong MPR capabilities. So first, we can observe that the DPP policy performs significantly better than the stationary randomized policy, and especially when the destination node has weak NPR capabilities. And we also have some other interesting observations. For example, when lambda is equal to 0.7, which means that the data arrival rate is very high, then when also the energy arrival probability is also high, then the average AOI will become independent of the energy arrival probability. It means that by having more energy arrivals, it will not help the energy harvesting node to achieve lower average age. So I would like to summarize my talk by the following conclusions. The first is that stochastic network optimization provides very useful tools for optimizing time average network performance with time average constraints. And we have showed that optimizing resource allocation only based on physical layer achievable rate can be suboptimal and inefficient when we consider random data traffic in wireless networks. And when we consider heterogeneous data traffic in a network, we can very often observe some interesting and non-intuitive interplay between different performance objectives. And last but not the least, age of information, which I believe is a very important metric for Internet of Things, will attract a lot of attention in the near future. And it is very important and very useful metric to characterize information freshness in some specific scenarios of IoT applications. So thank you for listening to my talk.
Thank you very much. It was exciting. Actually, I have a couple of questions on the follow-up, but since I've been having most of the time asking questions, let me see if somebody else has some. So in the audience, if you have any question, please feel free to, you can even unmute yourself and ask a question. Go for it. Okay, so while we wait for the others, so I had a question about the AOI part. So that is what you looked at the dynamic scheduling algorithm. And so that dynamic scheduling algorithm, the way you described it, seemed like a centralized policy, right? I mean, I need to have the information of both things.
Yes.
But before that, you also mentioned a scheme which was decentralized, where each of the S1 and the S2 kind of by themselves did not need to worry about looking at the state of the other, right? So
yes.
The two that you compare, this randomized one, was it that one? Like, you compared the decentralized with the centralized scheme?
Yes, I compared the centralized TPP policy with the decentralized random stationary policy that has been optimized. So
that
we have
the centralized one is better, right? Overall, in the way you put.
Yes.
So one question: if I did have more, so instead of S1 and S2, if I did have multiple, say, SIs, and if I now have, so then the load on the centralized scheme is quite a lot because it has to keep a track of a lot more states. Is there a performance loss if you have a lot of SIs in the distributed case? Like, does it fall off very quickly, or is it still a good enough scheme to keep in mind?
You mean a distributed
scheme,
the stationary randomized?
Let's say 100 queues, 100 SIs, let's say. And
yes.
Just because state is a bit of a problem for the centralized scheme, how bad does the decentralized one work in that case?
Yes, so first of all, with the decentralized policy, actually, even if we have more than 2 nodes, it is not guaranteed that we can find the optimal solution, the optimal transmit probabilities in closed form. So if we want to apply some other algorithms to find the optimal probabilities, then the complexity might be also very high, because if we cannot apply it directly by some closed form expressions, then we need to find some ways to find the optimal probabilities.
Okay. And is this the right way to understand? So the different things that you spoke about, and stochastic optimization being at the heart of it. One downside of stochastic optimization is the fact that I do need to know centrally all the states of everything. So there's no way to get into a distributed domain for stochastic optimization. Is there any theory there where you can maybe relax the full centralization and still get some interesting results?
That I am not aware of.
Okay, okay. Yeah, this is just because I'm not from the field, so these may be very basic questions. Just okay. And one other thing, so this is again based on my very primitive knowledge of age of information. So there is the metric of peak age of information, where instead of the time average, just look at the maximum peaks in all the plots that you had. Does that lead
Yes.
to a simpler and a simpler solution, for example? Because it's a simpler metric, I think, compared to age, average age. So,
Yes, actually, in the journal paper that we are preparing, we also studied peak age optimization.
oh, okay.
Yes,
And
it is. In terms of complexity, I would say they are very similar because the core part is just to solve an optimization problem that only has 4 different variables for the 4 different states. So you try the 4 different values and then you find the one that gives you the highest value.
okay. Okay. That is nice. Does anybody have any question to Zheng? It was a very nice talk, so I'll certainly learn quite a lot.
Thank you.
Okay. Yeah, I guess there are no more talks. I mean, so if this was happening in person, I would have asked everybody to clap. Unfortunately, that's not possible, but
Thank you.
Really
Thank you.
nice
That's
talk.
very kind.
Can certainly vouch for it. I mean, I was tuned, and I'm sorry again for the delays and the fact that you had to kind of tune in and give a live talk again. So I'm sorry, all your efforts recording it kind of gone waste. But yeah, it was a
No
very
problem.
nice.
No problem at all. I think actually the live interaction probably is better.
No, but I mean, it was helpful that you kind of planned for the worst case by giving us a recording. So yeah, thank you. I know how hard it is to make one.
Yes. I saw some other comments in
Yeah, there
the
was one question,
comment
yes.
sections.
Yeah. So this was actually just after you had started the MIMO part. So here was the question. So yeah, if the penalty uses expectation and V as a weightage, is not using any other stochastic measure such as variance or correlation, achieving a steady state stability. Okay, so I'm not sure if you understand this question, but Vijay, if you would like to clarify the question, you can unmute yourself and maybe ask your question again. So I'm not. Okay, he's copy pasted it again. Can you unmute yourself and ask the question? That might actually be better. This is for Vijay Bhaskar. Okay. Okay, apparently his microphone is not particularly good, so let me try to parse the question. So this was the part before the MIMO. He's, I think, interested in I'm not quite sure, but his clarification is what is the use of expectation? Well, yeah, I mean, would you like to take that? I mean, in whatever sense you can make of the question. I'm not quite sure if I can help you there.
Are
Otherwise,
you referring to the question about the penalty function?
yes, yes. So the question says that why not use some other stochastic measure as an objective in the penalty part, I think. So perhaps penalizing high variance or
I
something.
think he's asking about the expectation instead of some other stochastic measures.
Oh, so
Yes,
variance.
yes, because our performance objective is to maximize some long-term time average expectation, and our constraint are also time average expectation. So everything has this expectation in front, and then after some steps, we can, if I use another like variance, like what you said, then we will not be able to merge those things together because they are based on different measures. If we have the expectations, then the sum of the expectations is the expectation of the sum of 2 parts. So then we can just condition on the network state, and then we can just minimize some quantities in each time slot.
Okay, thank you. So does anybody have any other question? Yeah, he's just clarifying what he understood. Yes. So does anybody have any more questions? Okay. guess there are no more questions. So let's thank Dr. Zheng again. So wherever you are, I request you to clap your hand. That's what we do when somebody gives a presentation.
Thank you. Thank you
Thank
for
you, Dr. Zheng.
inviting me for this talk. I really
Excellent.
appreciate it.
Yeah. I hope you have a good time, and let's hope to meet sometime. I don't know if our paths will cross again, but
yes. So I will leave my email address in the chat, and then for those who have more questions, you may write an email to me, and then we can maybe discuss more.
Yes, I've left your webpage as well, and yeah, so some of you who would be interested in some of the work, she does a fair bit of stuff. So if you're interested in any of the problems she's been looking at, please feel free to look at her webpage. So I've put a link there, and like Dr. Zheng has been kind enough to share her email address, so feel free to contact her. Okay, thank you very much. I think it's time we can end the session. Sorry about the overtime, and thanks again for sticking by, Dr. Zheng. So
thank you too.
Yeah.
Have a good day. Bye bye.
Bye.